はその dreaming が忘れないででも気持ちは伝え
Chapter 8 One-Way Multivariate Analysis Manova One-Way. This chapter will guide you to run a one-way Manova task with a post-hoc task as well as how to interpret and report results. This chapter will also discuss the assumptions that need to be followed before performing this one-way Manova task. Introduction. The one-way multivariate analysis of variance, Manova, is an extension of a one-way ANOVA that combines two or more dependent variables versus just one lean variable in the one-way ANOVA analysis. What's distinguished between the analysis of ANOVA and MANOVA is the number of dependent variables. ANOVA has only one lean variable, while the MANOVA analysis has two or more learning variables. Example. You want to study whether there is a significant difference in terms of scores in one test between male and female students in three subjects, namely mathematics, English, and science. In this example, the student's gender is an independent variable IV, while the three subjects, which are mathematics, English, and science, are dependent variable DV. The assumptions to be observed in conducting the Manova analysis are as follows. The dependent variable dv must be at the interval level interval or the ratio level ratio. Independent variable iv must be categorical, i.e. at the nominal level or ordinal level. Variance, covariance is homogeneous in nature. No multicollinearity problems. The study and hypothetical questions for this example are as follows. So the study questions, is there a significant difference in terms of math, English, and science test score based on the student's gender? So the study hypothesis, hypothesis 1, there are no significant differences between male students and female based on math test scores. Hypothesis 2, there was no significant difference between male students and female based on English test scores. Hypothesis 3, there are no significant differences between male students and female based on science test scores. Open Manova data, click Analyze, choose General Linear Model, then choose Multivariate. Enter all three dependent variables, math score, English score, science score, in the dependent variable box, then enter gender into the fixed factor box. Click on Options. On the Display section, mark Descriptive Statistics, Estimate of Effect Size, and Homogeneity Test. Make sure significant level is 0.05, then click Continue and click OK. The Between Subjects Factors table only shows a male sample of 59 people and a female sample of 61. The descriptive statistics below show the mean score and standard deviation for male and female students for all three subjects. The English score for female student is 63.99%, which is higher than the mean score for male student of 61.45%. On the other hand, the mean score of the mathematics subject was also higher for female students at 68.26% compared to the male students at 64.32%. On the other hand, for science subjects, the mean score of male student was higher at 62.55% compared to the mean female score of 58.06%. The question is whether the mean difference in scores between this male and female student is significant or not. Refers to the box test of equality of variance matrices table. The significant value is 0.284. If a significant value is smaller than 0.05, it means we should reject the null hypothesis that states the covariance of the scores of the three subjects is different. However, in this example, a significant value of 0.248 indicates that we receive HO, which is the covariance of the score of all three subjects in the same between male and female students. This multivariate test table refers to the independent variable, example gender only. Please refer to the significant values for the Weeks lambda test. Is there a significant difference between male and female students based on the scores of the three subjects? In this example, a significant value is 0.09, which is smaller than 0.05. Thus, the null hypothesis, there is no significant difference between male and female students based on scores is rejected. This shows scores for English, mathematics, and science subjects vary significantly between male and female students. Refer to this Levin's test of equality of error variance table. The null hypothesis of this table is that the error variance of the learning variable is the same between the three groups. The error variance of the dependent variable is equal across groups. Please refer to the significant values of based on mean for all three subjects. If the significant value greater than 0.05 indicates the null hypothesis is accepted. For example, the error variance of the dependent variable is the same between the three groups. Based on the table, the based on mean significant values of the English score 0.437, the mathematical score 0.099, and the science score 0.429 exceeded 0.05. This proves that the error variance of the learning variable is the same between the three subjects. The test of between subjects effects table here shows the value of intercept, gender, and error for the math, English, and science subject scores. In this table, we need to focus on the significant values of the sexes only. The result from this table can be summarized as follows. Gender, refer gender-related lines only. So here, English score, the significant value of 0.244 indicates null hypothesis received. This means that there are no significant differences between male and female students based on scores for English subjects. For mathematics score, significant value 0.075 indicates null hypothesis received. This means that there are no significant differences between male and female students based on math score. And for science score, the significant value 0.011 indicates null hypothesis rejected. This means that there are significant differences between male and females based on scores for science subjects. The partial ETA squared column shows the effect size. If the value of 0.011 indicates a small effect between a male and a female, on the other hand, the value of 0.97 indicates a large effect size between male and females.